Yeah.
Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Dr. Marija Popović, who is a junior research group leader at the University of Bonn and also Cluster of Excellence FENOROB. So something about Marija: she did her master's in engineering in integrated mechanical and electrical engineering at the University of Bath in the UK. She then moved to Switzerland. She's actually an ETH alumni. She obtained her PhD from the ASL in 2019. And then before starting in Bonn, she was a postdoctoral research associate at the Smart Robotics Lab at Imperial College London. So her research centers around developing algorithms which enable intelligent robotic decision-making, including informative path planning, environmental mapping, and computer vision. I actually got to know her thanks to some lectures she posts online about general robotics topics. Those are great. You should look at them. And today she's going to talk about robot learning for adaptive informative path planning. This is an exciting topic for the audience of these Autonomy Talks, and that's why I'm happy to give her the stage.
Great. Thank you for this really nice introduction. It's a really pleasure to be here today, and hope our topics will be interesting for you. So today's talk will be about, yes, robot learning for adaptive informative path planning. And before I start, I would just like to give acknowledgements to the 3 PhD students in my junior research group, Liren, Julius, and Jonas, who contributed a lot to this presentation. So thanks, guys. Okay, so why do we want to use robots for sensing? Let's start here. So here we see examples where different tasks are done manually with humans directly in the loop. In these applications and many more, robots can make tasks simpler, faster, and more effective to save us time, money, and labor. In particular, they have high potential for tasks that involve mundane or repetitive procedures, need high levels of accuracy and precision, or transpire in risky or hazardous environments, the so-called dull, dirty, and dangerous tasks. However, as we know, making robots work in the real world is challenging. So in these scenarios you see on the slide, the robots need to reason about their surroundings, decide what to do, and plan paths to complete different missions, all the while operating in uncertain, complex, and dynamic environments. So there are some concrete examples. A UAV needs to decide how to monitor a crop field in a targeted way. This legged vehicle has to decide how to explore a completely unknown environment, such as the tunnel. And a surface vehicle has to decide how to move to gather the most valuable sensor information. In today's Autonomy Talk, I want to discuss how we can achieve these autonomous behaviors, specifically by integrating learning-based methods and robotic adaptive informative path planning algorithms. So let's start with a simple example of using a robot for sensing. So say we have this UAV, which we can see in a top-down view, that has to monitor a field of crops. Now, following a conventional approach, we usually generate a zigzag lawnmower type of path to cover the field at a fixed altitude, given the limited battery life of the UAV. Now, this strategy is very familiar, it's simple, fast, and also available in most commercial products. However, what if there are certain parts of the field that need to be inspected more closely? For example, what if we're interested in high temperature hotspots, weeds, or plant diseases, and getting more information in these areas? So the main drawback of using this passive lawnmower type of approach is that the entire environment is mapped at a fixed altitude, limited by the pre-planned trajectory. And because we don't know where these areas of interest, these diseases, these weeds are in advance, we can't improve mapping accuracy in these areas in a targeted way. Instead, we waste energy on exhaustive mapping everywhere the same. Through an active and adaptive informative path planning approach, we want to perform efficient targeted monitoring by allowing the robot to choose during the mission what to do and where to go next. We hope that by using this approach, we can adaptively focus on collecting higher quality data in the areas of the environment we find more interesting, leading to a much better use of the limited battery life. However, solving this problem presents several technical difficulties. So first, we need to decide how to model the environment and define an objective, measuring how useful future measurements are. Second, we need a path planning algorithm that allows us to balance between exploring the unknown environment and exploiting these regions of interest as they are found, And we need to generate paths that satisfy the robot's dynamic and endurance constraints. Also, if we want to replan adaptively during the mission, we want to make sure that our methods are computationally fast enough to be run on board and online. Oops. Oh, sorry, something happened there. Let me just go back. I think I somehow skipped to the end.
No spoilers.
I'm sorry, I hope you didn't lose the flow. So,
Okay.
An important part of both this mapping and planning processes is that we need a reliable model of the sensor. So we use this model to update the field map with new measurements as they are taken, and also to predict the value of future measurements the robot hasn't executed yet. So there's one example. When we have aerial imaging, as in this UAV example, a key trade-off lies in the fact that the UAV can see the same point on the field from different altitudes and therefore different resolutions. So we need to develop a model of the robot camera to reflect the fact that the higher up we go, the more we see, but the more noisy and the more uncertain our measurements are likely to be. And addressing all of these trade-offs makes the decision-making problem complex and computationally challenging to solve. So in today's talk, we're going to tie these three key elements together and develop a framework that is suitable for addressing these challenges we just discussed. So we want our framework to allow decision-making during a mission in uncertain 3D environments on computationally limited systems. And to achieve this, narrowing down in our talk, we're going to focus especially on learning-based methods. So these algorithms will allow us to push the boundaries of robot autonomy, which is what we're interested in this series of talks. So let's try to build up the structure of an autonomous system to see how this can be done. So say we have a robot, the UAV, equipped with a sensor, for example, a depth or multispectral camera, from which we can extract measurements. These measurements are used to construct a map of the environment of interest, such as the field. And here we might also have information from previous missions we want to incorporate. So during a mission, we have a planning algorithm that uses these environmental maps online to optimize trajectories based on a given objective. For example, efficient data collection. So this planning algorithm takes as input the current state of the map, so the current belief of the environment, the robot pose, and the budget remaining for the mission. So how much battery time is left, for instance. Here, the key ingredient is the so-called utility function, which is used to reflect the aim of the mission. So what we want the robot to achieve. And we use this to measure how valuable future measurements are. Now, based on the planning output, we get action sequence, for example, a trajectory that the robot executes. Now, based on what new information is observed, this closes the loop between action and perception, allowing the robot to act based on what it sees. So essentially, in this framework, the executed action influences the next one, the next sensor information, and the robot pose, as shown by these arrows. So for each of these components, traditional and most current methods rely purely on models. So there's some examples of models. For mapping, we could have a volumetric representation of the environment, such as an octomap shown here, which captures spatial occupancy. To calculate the utility or the value of future measurements, we could have, for example, a projective camera field of view. And we could measure how useful future measurements are using such a simple distance-based model to predict how the map will evolve when we take a measurement in a certain location. And finally, for planning, we can use a sampling-based strategy. So we sample new configurations in the environment based on a robot motion model, and we evaluate them based on a cost function, for example, to explore the environment as quickly as possible. And then we pick the best one. However, just relying on models inherently limits the informative path planning approach because we cannot easily transfer to new environments, and we're limited by the quality of the models. So to address these issues, we're going to try to bridge the gap towards modern learning-based approaches. And we hope that by doing this, we can reduce the dependency on prior knowledge, increase the robustness of the algorithm to disturbances and variability, adapt to unseen environments with new environmental conditions and possibly unmodeled objects, And finally, we hope to improve the computational efficiency, which is important for real-time applications. So this is a very broad field of integrating learning and adaptive path planning on robotics. And I want to dissect it into different topics that we'll discuss today and present some of the research that we have done in each of these areas. So we're going to look at reinforcement learning, active learning, neural representations, and supervised learning applied to the adaptive path planning problem for robotic data collection. So just to make it clear, here we don't want to completely replace the model-based approaches, but we want to see and try to understand where learning-based methods actually make sense and how we can bridge the gap. So let's start with the first topic, reinforcement learning. So what do we actually want to do? How can we formulate our problem? So going back to our initial UAV terrain monitoring example, we focus on what is formally known as the adaptive informative path planning problem. So essentially, if we have this UAV flying over a field, we want to maximize the information value in the new measurement it contains, subject to a budget constraint. So in other words, given its limited battery life, how should the UAV fly to get the most useful measurements from the environment? For example, inspect the plants on a field more closely. And specifically, we call our problem adaptive because of this information value function. This I not only depends on where we take the measurements, but also on their value. So for example, we might have an objective that says we want to map a focus on vegetation as quickly as possible. And this motivates the needs for adaptive replanning during a mission. So this problem is challenging for three reasons. So first, we need to predict the value of future actions without the robot actually executing them. Second, to decide which one is best, we need to be able to evaluate many such actions in a high-dimensional problem space, which can be computationally expensive. And we need our algorithms to be fast enough to be run online on resource-constrained platforms, such as small UAVs. So focusing specifically on this aspect of computational efficiency, I want to introduce a deep reinforcement learning or RL approach to address this problem. So the main idea of the approach is as follows. So we have a neural network, which we see on the left, which we train to learn the next best data gathering policies. So how the robot should act next. So we train this network in a realistic simulation environment shown on the right. So we simulate many realistic UAV terrain monitoring episodes here, and we use this to train our network. So the network learns to predict where the measurements with the highest information content are likely to be found. And the reason for doing this is that when we decide where the robot should take the next measurement, we don't need to predict many future actions and forward simulate into the future using sensor models. We have an already trained network, which we can deploy in a simple forward pass. So we evaluated the approach in simulation, comparing against different baselines. So we compared against the CMAS, which is a state-of-the-art adaptive informative path planning method, Monte Carlo tree search, coverage lawnmower type planning, which we saw in the initial slides, and random motion. So on the left plot, we can see how the map uncertainty reduces over the mission time. And on the right, we see a runtime comparison of different online strategies. So looking at the plots, we can see that the RL-based method reduces map uncertainty quickest, but most importantly, it leads to significant speedups for online replanning. And as we said, this is because the network is trained offline and we just need the forward pass to generate the next plans. So we validated the approach using real-world thermal data. So we flew a UAV over this crop field, as you can see, and we obtained thermal imagery and stitched it together into an orthomosaic. And given this input data, we defined an objective where the goal is to map the high-temperature areas as quickly as possible. So in this setup, we compared how the RL-based approach compares against coverage type of planning. And we can see that by replanning online, the RL-based approach can reduce map uncertainty much quicker in these high temperature areas of interest because it can actually replan online based on what the network was trained. We can confirm this also qualitatively. So here is an example trajectory flown by the UAV using the RL-based approach. And we see that once it has explored the environment and discovered this warmer high temperature side, the UAV stays there to collect more measurements as we would want. So motivated by this promising results, we then extended this approach to multi-UAV applications, which consider different UAVs or agents in a similar problem setup. Now the problem becomes trickier because we need to not only decide where an agent should measure next, but how we can achieve cooperation among them while also replanning effectively. So as in the single agent case, the logic here is quite similar. So we want to have a neural network trained offline in simulation and deploy the already learned parameters during the mission in an efficient way. So specifically in the approach I want to introduce, we considered doing this using a state-of-the-art multi-agent RL algorithm called counterfactual multi-agent policy gradients, or COMMA. In this figure, we overview how we adapted COMMA to the multi-UAV terrain monitoring application. So as we can see on the left, each UAV stores its own local map containing the information of all of its measurements and those communicated to it by the other agents. So everything it knows about the environment. And then the next action, or the policy, is obtained using a forward pass through this green actor network. So how do we train this network? So following the principles of COMMA, we use a centralized critic, shown here in the purplish color. So this critic is used before a mission during the learning phase based on a global map of the environment, which contains information about all of the agent's measurements. This setup, using a centralized critic and decentralized actors, allows us to use what we call counterfactual baselines during trainings. A counterfactual baseline is an intuitive concept which just measures the value of each agent's measurement to the overall objective. So it tries to assign more credit to agents that have performed better. And this allows us to nudge learning in the correct direction so that we can cooperate more effectively. So far, this credit assignment problem was only considered in classical RL scenarios. For example, the original COMMA was actually about a StarCraft game, but specifically we want to apply it to this multi-agent UAV use case. So as before, we evaluated the approach in simulation against different benchmarks. So we have the COMMA-based approach in green compared against an information game-based strategy, a sampling-based approach. Coverage again, and random motion. And on the left again is the map uncertainty evolution over time, and on the right is the error. And these results show that COMMA does indeed allow for improved coordination and leads to fastest reductions in map uncertainty and error, which motivates the use of learning-based strategies for more effective coordination for this problem. Taking it one step further, just like in the previous work, we also deployed it on the same thermal data obtained from the real. Quick sketch of what 4 agents do when faced with this problem. Now, these agents were trained in simulated environments, but they were able to we were able to deploy the trained network in simulation into this realistic data. And as we would expect, the agents collect more measurement on the high temperature side. If you're interested in this work, as we just discussed, you can visit us at IRIS next month. It will be presented there for more discussions. So taking this further, the next step, we're investigating how to extend such approaches, such as COMMA, to 3-dimensional environments, for example, monitoring orchards. And on the right is a quick visualization of a simple simulation environment that we're building that could be used as the basis for training RL-based agents in this approach. Now, this is very preliminary work, but I wanted to give you some insight as to the progression of these types of learning-based approaches for environmental monitoring scenarios using UAVs. So with that, we can move to our second topic, which is active learning. And here we're going to slightly switch gears. And instead of discussing how we can learn next best data gathering actions, we want to see how we can actively learn about a new environment to improve robotic vision using informative planning. And here we're going to focus on a slightly different application, which is aerial semantic segmentation. So as we know, semantic segmentation is very important for mapping and observing the Earth, but training traditional supervised deep learning models requires a large amount of high quality labeled data, which can be very tedious and expensive to generate. So there are some examples from an urban data mapping data set called ISPRS Potsdam, where we can see very fine details that require significant human efforts to label correctly. So to address this challenge, we propose a new approach for using autonomous robots to collect useful data for human labeling and network training. So here is a sketch of how the approach works, focusing on UAV-based applications again. So we start with a pre-trained segmentation network deployed on a UAV. During a mission, the network predicts semantic labels and model uncertainties in images, and we project them onto the ground to build global maps capturing these variables. So here we see a representation of the whole global environment that we want to map. So based on the model uncertainty, we plan paths for the UAV to collect the most informative data to improve network performance. So a key aspect here is that we leverage ideas from active learning. We want to collect the data samples with the highest model uncertainty, reasoning that these examples are the most difficult to learn and thus hold the most information value when added to the existing training set. So once the UAV executes its path, informative path, collects new images, we pass them to a human annotator who performs human labeling, and then we retrain the network after the mission. And their motivation is by using adaptive informative planning in this way, we want to reduce the total labeling effort when compared against exhaustively labeling all of the images. Now, this is a very general framework that combines aspects of adaptive robotic informative path planning and active learning. But there are several open questions to be asked here. So which kind of planning and mapping algorithms do we want to use? And how can we measure the active learning objective or the so-called acquisition function? So how do each of these elements play together and influence the overall active learning performance of our framework? So in a recent project, we proposed different strategies for each of these elements and then conducted an analysis to assess what their implications are in this robotic context. And I want to share with you on the next slide some key results for this robotics application that I think are interesting. So for these experiments, we used the ISPRS Potsdam dataset, which we saw on a few slides ago as an example. And we want to measure active learning performance, how many images here on the x-axis need to be labeled to achieve high performance on the y-axis. So first we did an experiment to compare different planning strategies. So we modified the planning algorithm. Steeper curves here indicate better performance, so pushed more towards the top left. So here we compare coverage, which is the lawnmower type of approach, against an image-based strategy, which only executes local plans based on adjacent motions, and frontier and fixed horizon, which are two global path planning strategies relying on the map representation. And we can see that the planners either outperform or perform on par with the baseline. In particular, the blue and the orange, the orange one actually outperforms the local planning scheme in this setup. So in the same setup then, we did an experiment now focusing on the mapping component using the same planning strategies. So what we do now is we continuously update the prior map knowledge using our approach and see how this influences performance of the different planners. Promisingly, we see that this pushes most informative planners up in active learning performance, such that indeed now all planners reliably outperform the planning baseline. And now we can safely say that the map-based planning outperforms the purple local planner, which also supports the benefit of having this continuously updated map knowledge and using all the information that we have. So then to get more insight into these findings and develop intuition, we also compared active learning performance per class. So for each different individual class shown here in the different colors found in the Potsdam dataset. And we narrow it down by comparing the coverage-based baseline against a frontier-based approach, which performed best earlier. We can confirm that our planner, which relies on adaptive informative planning and the active learning objective, reliably outperforms the baseline for almost all of the classes, which confirms that it can capture this complex task-dependent model uncertainties, regardless of the training data support for each of these classes. So that's for the mapping and planning components. Next, we study different methods of calculating the active learning acquisition function in the informative planning objective. So just to recap, as I mentioned, in our framework, we want to guide our UAV to collect the most informative or the most uncertain images, representing the most difficult examples for the network. So in deep learning, there are different ways of calculating this type of model uncertainty that we're interested in. And our goal was here to investigate them in a robotics planning context for data collection. So we explored a deterministic non-Bayesian objective function in ORIGE against two different Bayesian uncertainty measures, using Bayesian ensembles in yellow and Monte Carlo dropout in blue. And again, we plot the same metrics to see how the different information functions compare against each other. So as you can see in the plots, the Bayesian uncertainty measures perform better than the non-Bayesian deterministic objective, which only looks at the prediction entropy over the labels. And this confirms what we know from literature, that non-Bayesian uncertainty typically tends to be globally poorly calibrated with respect to these Bayesian approaches. And the main finding here is that this results also hold true in the robotics scenario. So we can understand this better also by looking at some qualitative results of error and uncertainty using the different approaches. So from left to right, you can see the RGB input to the network, the ground truth obtained from the dataset, the semantic label prediction provided by the network, error with respect to the ground truth, and model uncertainty computed via either the deterministic non-Bayesian approach or the Bayesian ensemble on the bottom. And if we compare error and uncertainty and how they relate to each other, we can see that the deterministic entropy only weakly correlates with the prediction error here. And this explains those quantitative results why active learning performance tends to be worse. Now, so far, we only presented these findings on the Potsdam dataset. So this is this dataset that we looked at, shown on the top right, which is characterized by a very dense spatial distribution of the classes, such as building and roads. And then we asked, do these findings also hold true for different environments? So we tested on another dataset, which is publicly available, called RIT18. This is a land cover domain, which is very different. As you can see, it has different large connected components with more occupying more area in the pavement. And there we see the same active learning performance of the different planners. So we notice very similar trends as for the Potsdam dataset, especially the global map-based planners tend to perform even better because they can cover these large connected regions more quickly, as opposed to using a simple local-based strategy, which can only afford incremental movements. So from this, we can also deduce that the structure of the environment plays a big role in terms of active learning performance. And finally, moving towards more realistic scenarios, we tested our approach in Flightmare, which emulates UAV physics and has more similar to real-world deployment conditions. Again, on the top right is visualization of the environment. And we specifically consider this industrial type of scenario, which also offers the opportunity to study a different application domain. And again, we can see from the active learning results that global map-based planning, again, outperforms local planning and the random baseline, which validates the approaches on a third dataset. And so together, these findings tie together these different components of the framework I presented, the mapper, the planner, and the learner part, in one single pipeline and shows how we can use them to improve robotic vision in an autonomous way in new missions. So in a follow-up early work, we're also studying the effect of how to select human labels rather than densely annotating them. So we saw already what we can do with the targeted selection of images via informative planning, but can we use smart strategies to also figure out how to select the most useful pixels on an image level for labeling? So here we did an interesting first experiment using our informative planner, changing how to choose which labels to pass to the human annotator in images. So in different colors there, we can see different human labeling budgets on the x-axis, ranging from around about 0.05 in orange to about 6% in the dark red. So we study a variation of different human label budgets, and we compare with the solid line what happens if we randomly select pixels given this budget, and the dashed line, which is using a targeted strategy for selecting human labels based on state-of-the-art semi-supervised learning methods from literature. And the very interesting finding here is that even in this robotic setup, selecting pixels in a targeted way leads to better performance, especially when we reduce the human budget. So this tells us that actually it's also not only important which images collect, but which pixels we choose to label in those images that have been collected. And we're looking at now how we can incorporate some of these ideas into a semi-supervised framework to benefit both targeted planning on the global level, as well as targeted human label selection on the per pixel level. So that was about active learning, hinting towards semi-supervised learning as well. And the third topic I want to discuss with you is neural representations for informative planning. So in this topic, we're going to consider a slightly different problem setup to the UAV-based monitoring scenario, which is more in line with neural representation literature. So say we have a 3D object of interest that we want to reconstruct. So here, this Buddha statue and an RGB robotic camera setup. So in this figure, we can see the different pyramids, which represent possible viewpoints for the robotic camera. And the setting, our goal is to iteratively select the next best views to maximize our understanding about the object. So we want to position the camera around it so that we can collect the most informative images. So this is known as what you might be familiar with, the next best view planning problem, which is very related to the informative path planning problem. So how can we solve this problem? A common strategy is to use a map representation of the object. For example, a surface, mesh, or volume, as we see in the examples, and then we look at the current map state and plan next best views using a predictive sensor model. However, one can imagine that for larger and very detailed environments, maintaining such large maps, high fidelity information becomes very memory and compute consuming. So to address these issues, we propose an approach for next best view planning based on learning, specifically uncertainty-guided image-based rendering, that only uses a network to determine the next best view without maintaining this explicit map representation. Now, without going into too many details about the underlying perception, image-based neural rendering is essentially a representation that conditions the implicit representation on image inputs after retraining on different scenes. And this allows us to generalize to new environments and achieve novel view synthesis from a sparse set of views. So this has been quite the trend recently in terms of reconstruction, and our idea here is how can it be used for planning. So in our framework, we first sample potential viewpoints around the object, so these pyramids. And then for each candidate, we render the RGB and the uncertainty using our image-based neural network. So as in the active learning problem, uncertainty tells us something about how informative an image is. So high uncertainty means that more images here would be useful so that we can reduce it and achieve a more certain representation. So based on this reasoning, we select the most uncertain viewpoint candidate we have sampled, and the camera moves to take an image there. So we store all the images we have collected thus far, and we use them to condition our network for future iterations of the planning loop. So we repeat this process iteratively until a measurement budget, for example, a cap on the number of images, has been achieved. And this way, as we said, we can plan without relying on this compute and memory-intensive explicit map representation, but only on periodically retraining and without periodically retraining the network. So here are some results that we performed using the DTU dataset of different objects. So what we want to do is evaluate the benefit of using uncertainty in image-based neural rendering to guide the selection of next best view reference images. Now, DTU has pre-recorded poses, and we assess the different strategies for evaluating reference images among these fixed candidates provided by the dataset. So here we compare the uncertainty-guided approach in red against an approach which selects the next candidate based on maximizing the views to the current position, so something like a coverage type of approach, as well as random motion. And we can see that using uncertainty consistently leads to improved quality of the image rendering metrics for this unselected test scenes in the dataset. So to remove this constraint of having prefixed poses to choose from, we built a simulator based on ShapeNet models to mimic also a more realistic robotic setup. Now we have, as we said, a continuous action space, which allows for more flexibility when picking new viewpoints. And here, indeed, we observed even more pronounced improvement when using the proposed uncertainty-based image rendering approach. So there are some presented at IROS. Here we see a comparison of different approaches using one of the models from the data set. And we can see using the image-based neural rendering approach, the third one leads to much sharper rendering, as reflected also in the quantitative metrics. Now, in a similar setup, I also want to share some ideas on how we can apply well-known supervised learning methods for a similar next best view planning problem. So one interesting observation that comes from reconstructing single objects is that the number of views that we need to reliably reconstruct something using a neural implicit representation really depends on the complexity of the object. So there is a very simple and intuitive example where we have two different objects of different complexities. So on the top, we can see a not very colorful and with simple geometry model of a monitor. And on the bottom, we can see a colorful and geometrically complex flower pot. So using a neural representation, we want to see what happens when we try to reconstruct two of these objects using 20 and 50 different views. And we can see the configuration of these views on the right-hand column. So on the first and second column, we can see the results for these two objects. And intuitively, we observe that 20 views is enough to reconstruct the simple monitor, but it's not enough, and we observe blurriness and artifacts when we only use 20 views for the flower pot. And with 50, however, we achieve a pretty good reconstruction of the flower pot as well. So the question that we want to ask is, given this heterogeneities between different objects and their complexity, can we learn how many views are enough if we only have the given object at hand? And this is what we're going to try to apply supervised learning for. So here's a brief insight into the supervised learning approach. So we have a data set of different objects, and we labeled the number of views required to reconstruct them. So we saw at which point the reconstruction performance converges. So we use this data to train a neural network to predict the required number of views for a given object. And then what happens during a mission, we first acquire 3 different initial views from different angles to get an idea about the object structure. And then we input these views into our network called PRV, prediction of the required number of views. And this network, which is trained, outputs a single number, which is the number of images needed to reconstruct that object. And this intuitively correlates to the complexity. And then we take this number and we apply times view space to get the geometric configuration of how to distribute these views. So we get the global path that the robot should execute, which is here in the pink. And then during a mission, the robot executes this path. At every viewpoint, it stops to collect the measurement. And after the mission, we get all the images and the associated poses, and we train a neural representation for reconstruction. So here's a hint as to what this results look like for next best view planning with complex objects. So I'll present objects of relatively high complexity so that we can appreciate the differences between them. So in the first and second column are different objects. So we compared how our PRV-based approach, so this is the red and the blue, compare against uncertainty-based next best view baselines using the same budget as predicted by our network. And here we plot how the image quality metrics based on 100 test views evolve over the camera movement cost. We can appreciate that planning based on the predicted budget with the view configuration allows us to achieve superior performance compared with less movement cost compared against the baseline. And this is because learning allows us to predict and use the budget more effectively and effectively adapt to the object's complexity. And this is an interesting application, I think, of how we can use supervised learning specifically for the budget part, which is often assumed to be just fixed or given in the literature. We can actually figure out how many views do we need to reconstruct if we have a given object. So this brings us to the end of the 4 topics that I wanted to discuss today. And I'll just share a quick recap of everything we have covered and finally some take-home messages from today's presentation. So I started with an introduction to the adaptive informative path planning problem, which is important for robotic data gathering missions. And then we looked into how we can incorporate different learning-based methods to this problem, including reinforcement learning, active learning, neural representations, and supervised learning in this approach. Based on the findings and the approaches I presented today, I would like to emphasize that it seems that learning is quite widely applicable for the adaptive informative path planning problem, and in some situations can really facilitate data gathering and accelerate both performance and computation in different applications. An open question, however, that I want to point out is how we can integrate model-based approaches with the learning methods. So when is it actually justified to use learning, and in which situations is model-based planning enough? How can our models complement our learning methods and so on? So that's something to think about in the future work. And finally, I think that one interesting direction, an interesting trend in which this line of work will take us is also exploring more complex scenarios, to moving towards 3D environments, as I hinted at already, and figuring out how to use a semantic in an informative way to guide data gathering based on a holistic understanding of new scenes, and eventually moving also towards open world scenarios. So thank you for your attention. And now I hope I was on time and happy to take on any questions you may have.
Thank you, Marija. Perfect timing. And thank you for the great talk. Let's open the stage for questions. You can either raise your hand and directly ask or write in the chat and I can read the questions for you. So who wants to be the icebreaker? Actually, I am, okay, I'll start with the icebreaker one. So you showed a lot of results and also quite different applications. And in some cases, the results were, as you pointed out, were very good. And I wonder, is that an intrinsic feature of the applications you have chosen? Or you think that these results would extend to other applications that you haven't touched on?
So from our finding, and this is kind of like a general comment of using this adaptive planning strategy, that we find span across the different scenarios that I presented as well is that the findings are quite promising for situations where we have an uneven distribution of information in the environment. So I presented a lot of scenarios where we're interested in mapping certain parts in a targeted way. And I think for this case, it does make sense to do something more intelligent and enable this type of decision making. However, one disadvantage that we found is that coverage-based planning and exhaustive mapping is actually quite good when that is our goal. So when we're interested in, we have kind of a uniform distribution and we want to map everything in exactly the same way. So if we have kind of complex problem scenarios that justify these types of approaches, then I think the findings can be quite promising, but it, as you point out correctly, it really is an aspect of the application itself. I hope that makes sense.
Yes, totally. Because I was wondering whether you thought about applications in which you are considering, of course, you are already considering situations in which you have multiple agents interacting. But for instance, whether one could embed what you're doing into game theoretic motion planning or these more recent works on collaborative agents.
I think that's quite interesting. It's not something that we have looked into so far. So mostly we have been looking at this kind of multi-agent RL approaches and their value. But I think maybe merging these two fields of research could be quite promising.
Okay.
We'll probably have to read up a bit more.
Yeah, we can touch base at IROS if you want. So there is a question in the chat from Jonathan asking, in the multi-agent RL setup for adaptive informative path planning, are the agents trained to avoid collisions?
That's a very good question. So what we actually do is design, so we assume that we have perfect localization uncertainty of the agents. And so by the nature of the way that actions are executed, we don't allow agents to move into the locations where there is already another agent. So we kind of mask out that action. So basically it's in the assumption that you know where all the agents are at, and it's a hard constraint on the algorithm. But say that you had some sort of localization uncertainty or anything that could influence this, then you will need more sophisticated methods and probably some kind of local planning to check that what you think you're doing is actually correct. Thanks for the question.
Jonathan, I think this answers your question. In case you have a follow-up one, just write in the chat. Any other question from Marija? Here we have a shy audience. Maybe, so I usually ask if you were going a bit fast in the conclusions because you were at the end. Do you want to maybe extend a bit more on one of the three future challenges you mentioned? Is there something more you want to say about them?
Yeah, I think so. Let me try to think of something that could be most interesting for you. I mean, I think that one of the interesting things for me personally is also how to use semantics to guide our informative path planning. Because, for instance, in some of the results I presented, we were just measuring like a continuous distribution, such as temperature. And maybe if we could incorporate something also about the structure of the environment or what kind of objects are likely to be there, that could further improve our understanding. And I think that's especially true in more complex, in scenarios with more complex structure, such as 3D, which have also partial observability, occlusions, and so on. So if we have some more holistic understanding, how do we put that into our existing algorithms? How do we use that for information gathering? Can we measure semantic uncertainty? How does that influence? And there's a lot of open questions, I think, to be explored there. I think there's another question in the chat.
Yeah, exactly, which connects to what you just said. Suchetan asks, in case your work has to be translated to a ground-based robot exploring a 3D environment, is there code and datasets available in order to compare with existing works?
So we have code available for the terrain monitoring project, so the UAV with a top-down facing camera. We haven't worked with ground robots so far for this application, applications, but it is somewhere in the work down the line, because we also want to look at heterogeneous platforms. But so far, we can only provide the code and the data to generate these results for the UAV based scenarios. So if that's helpful for you, then I can also send it.
Okay, perfect. I don't see any other question, but I think yeah, exactly. Maria just shared her email.
Yeah, I just shared my email in case you're interested in the code, so that I don't look for it now, and then we can sync up on that later.
Very good. I was about to suggest this. All right.
I think it would be the easiest way.
Yeah, I agree. All right. I think that there are no other questions. We can leave Maria to her evening. Thank you very much again for the
Thank you
for the great talk, and also looking forward to discussing more next time we see each other. Very exciting.
Yeah.
Stuff.
See you next month.
See you next month. Bye bye. Take care.
Bye.
Bye-bye.
Thanks.